So today we're going to learn about some basic applications. Most of the applications fall in chapter 4. Did you guys see that you have a quiz tomorrow? I think you have a notebook check. I think there's still a notebook check and a quiz. The best way to be prepared for the quiz is to be prepared for the notebook check.
Yeah, that's what you do. Six.
Oh, so you could be less prepared for the quiz by not having all the work done?
I mean, it just meant less work tomorrow, but I can't prove.
So this is not actually on the quiz. It says it's 3.2 to 3.6. This is 3.4. The only question I had for the quiz, I decided was a little bit too difficult for this point. You'll be able to do it later in the course, but we're not going that deep today. So the first question it asked me to do is find the area or the rate of change of area of a circle with respect to radius. So A of r, area of a circle is pi r squared, right?
Right.
With respect to radius is why I put it as A of r, meaning my independent variables are. So finding the rate of change just means the derivative. With respect to r means it is dA dr. That r is my independent variable. You're like, can all my problems be this easy? The answer is not all. It asks me then to find the rate of change of the area at r equals 5 and r equals 10. Equals, I plug in 5 and I get 10 pi. When I plug in 10, I get 20 pi. Now here is where it gets interesting. If r is measured in inches and a is measured in square inches, what would be the appropriate units of dAdr? Inches squared per inch. You cannot call that inches because it's the rate of how fast is the square inches increasing for every inch of radius. A little bit bizarre, isn't it, that that unit does not simplify out? That's a little different than we've been doing. Okay, can you guys flip to page 124? I'm going to look at example 2. So, some useful information to know. We are going to represent displacement with S or position. And we're about to do a little bit of physics with this. ds dt, and often S is an equation of time, right? Is velocity. So the derivative of position is velocity. the rate of change of position. What's the rate of change of velocity? Acceleration. So that is important information, that which is the second derivative of position. So looking at example 2, figure 324 shows the time to distance graph of a 1996 Riley and Scott MK3 Olds WSC car. The slope of the secant PQ is the average velocity for the 3-second interval t equals 2 to 5. In this case, about 100 feet per second or 68 miles per hour. The slope of the tangent at P is the speed of the automobile at 2 seconds, about 57 feet per second or 39 miles per hour. The acceleration for the period shown is nearly 28.5 feet per second during each it should be feet per second per second. They say during each second, which is estimated to be about 0.89 g, where g is the acceleration due to gravity. The race car's top speed is estimated at 190. Okay, so you can look at that, and they didn't give you a graph that's specific enough to actually find those slopes, right? They didn't give me the function, they just gave me values. So the slope of the tangent line at P, the instantaneous velocity, is 57 feet per second. That's how fast it's going at that point. Reading a velocity graph. This is one of the harder things. So a student walks around a motion detector and records her velocity at 1 second intervals for 36 seconds. She stores the data in her graphing calculator and uses it to generate a time versus velocity graph. Describe her motion. So they're using a graphing calculator. We'll actually do this with carts and physics next week. So what does her motion look like? So if those are 36, we've got 2, 3, 4, 5, 6, 7, 8. So each one of those is 4. Do you know how I got that? So it's got this label below it. The bottom one is X. So I knew that the end was 36. And I counted the number of dashes. I got 8. There's 9 gaps. 36 divided by 9 is 4. So what is she doing for the first 4 seconds? She's speeding up, walking away from the detector. Because remember, this graph is velocity, it's not position. So she's increasing her speed, walking away from the detector. For the next 4 seconds, she's walking away at a constant speed. And then she's still walking away from the detector because the velocity is positive. But she's slowing down. Okay? 0 to 4, speeding up, walking away. This takes practice to get used to reading these graphs.
Not even to buy some. That was a very good. Uh,
8 to 12, still walking away. At 12, the student turns around.
but
I guess no, that's more like 14. This shouldn't be 12, this should be 14. And then 14 to I think 20. Walking a walking back at an increasing rate. Does that make sense? It's negative. So they're walking in a negative direction. I'm going to assume they don't go past the sensor. The way to figure out how far they've gone is to find the area under those curves, which involves integration. That's derivatives in reverse. That's later in the course. Okay. And then from 20 to like 26, they're slowing down. Looks like they're stationary from 26 to 32 or something like that. And then they walk away at an increasing rate from 32 to 36. Does that make sense?
yeah.
When their velocity is, they're only stationary when the velocity is zero. When they're at this top part of the graph here, that is not stationary. It's a constant rate of moving away. Means they're not accelerating, but they're not stationary. They're only stationary if they are on the x-axis. Come on, scroll. There we go. So, couple important things. You know from physics class that G is 9.8 meters per second squared.
I know.
You might know this one, but this is what we'll mostly be using in this class. G is 32 feet per second squared. So flip over to 126. So, modeling vertical motion. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. If it reaches its height of, this is the equation, okay? Now it's nice enough to give you the equation. They usually do in a calculus class. Says, how high does the rock go? Well, there's two ways to do this. This is a parabola, correct? You can find the vertex of the parabola using negative b over 2a. Or you can find when the velocity equals zero. because at the top of its motion, the velocity was positive going up, it's negative coming down, it's zero at the top. So I'm going to do that way because that's kind of the new way.
Yeah.
So I take the derivative.
But
I set it equal to zero and I solve this will give me t. It did not ask me though when it asked me how high. So I need to get S of 5.
are these nations? No, no, no.
I guess I just squared 5 right away. And this equals 400. This rock goes 400 feet in the air. Get out of the way when it falls. I mean, it was launched with 160 feet per second. It asks, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up, on the way down? So, in order to solve this, I need to take the original equation. I need to set this equal to 0. And I'm going to put it in the normal quadratic order.
Look at me.
I can factor out a 16. Actually, I'm going to factor out a negative 16. And that factors into t minus 8, t minus 2. Meaning my solutions are t equals what?
8.
And 2. So it's at 256 feet at 2 seconds on the way up and 8 seconds on the way down. No, it did not ask me for those. Oops, that's a squared. It's not a very nice squared. It asked me for the velocities. And this is negative 96 feet per second. V of 2 is positive 96 feet per second. Notice that they're the same speed. They're just a different direction. That makes sense? No, wait. We should probably go through part C. What is the acceleration of the rock at any time? Well, that'd simply be the derivative of velocity, right?
Yeah. This is easy.
Yeah, it's the acceleration due to gravity. That one's really easy. You'll find oftentimes like parts C and D are easier. When does the rock hit the ground? Well, you could set this equal to 0 and solve, and you get 10. You could also recognize that it's launched from the ground. It takes 5 seconds to go up. How long is it going to take to go down? So it hits the ground at 10 seconds. So, and like I said, you could have found the vertex of this parabola with, negative b over 2a and plug it in. like you did in, I think we started doing that in integrated too. You definitely did that in algebra too. We did a little bit of it in pre-calc. So there's multiple techniques. I wanted to show you the velocity one because that's the new one.
Kind of,
You kind of prefer the new one? I think I do too.
either way, it's been super difficult, but.
At this point, yeah, none of the ways are difficult. So, derivatives in economics. If you see the word marginal, so if I ask you for the marginal cost, that would be the cost of the derivative equation. Marginal, the other way of thinking it is rate of change.
Is it?
I'm gonna review it into the,
Yeah.
okay, where is this?
I'll get it in a second. So we're given this for a cost equation.
Isn't he called that to late? Ah.
And it gives us this for revenue equation. Do you guys know the difference from cost and revenue?
We should. I believe I.
Revenue is profit minus cost. So it's how much money you actually make.
Those so nice. But
Okay. So it's supposed to cost blank to produce X radiators when 8 to 10 radiators are produced. That revenue gives the dollar revenue for sell X radiators. Your shop currently produces 10 radiators per day. Find the marginal cost and marginal revenue. So marginal cost is simply C prime of X. Such a nice, easy derivative. Marginal revenue. It asks me to find them when they're 10. C, so C prime of 10 equals 3 times 10 squared minus 12 times 10 plus 15. That's 300 minus 120 is 180 plus 15 is 195. Three times 10 squared. So that's 300 again. Minus 60 is 240 plus 12 is 252. So that is the rate of change of cost to produce a radiator, the rate of change in revenue to produce a radiator when I'm producing 10 radiators. The calculus here is really easy. The interpreting is the little bit harder part. Does that make sense? And that's the end of your lesson.